Good. All right. I'll begin. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just be with us today. Help us to just understand a little bit more about your creation, about Simpsons rule, and trapezoid rule, and errors and such. And I also pray that we'd be able to answer any homework questions that students have today, Lord. In your name I pray. Amen. So let me just I'm gonna take your homework questions after I've done this a little bit. Partly because I've got this stuff on the board and I might as well just talk through it with you guys. First of all, one of the first orders of business is at the end of last class, we made the correction to the Weierstrass substitution. Thanks to the gentleman in the front row. And then I did this integral, but when I did it, I neglected this square root of 3, I believe, and I might have put a third here. Anyway, the details weren't quite right on that integral at the end. So here's the correction to that. So we start with the Weierstrass substitution, right? And clear out the denominator by multiplying by 1 plus u squared. That gets me to the integral of 2 du over u squared plus 3. We did that correctly last time. But then I just I jumped the shark or whatever, going from here to here. I just tried to guess it, and I should have actually worked out the details. If we do this trig substitution, u equals square root of 3 tangent theta, then u squared plus 3 is 3 secant squared theta, and du would then be square root of 3 secant squared theta d theta. So if I make this trig substitution, plug it into the blue equation here, then what you get is you get 2 secant squared upstairs and you get 3 secant squared downstairs. The secant squareds cancel, and you're just left with 2 root 3 over 3 d theta, which integrates to this, right? Then, of course, I have to undo the theta. Solve this for theta. We get what? Theta equals to inverse tangent of u over root 3, right? And then finally, I have to go back and put back in the Weierstrass substitution, and there is the answer. I do think that this could be improved through exploiting the various trigonometric relations that exist between x over 2 and the tangent and the sine and the cosine in this triangle. Like, there's probably a way of simplifying that, but I don't know. I haven't tried to go further than this. I have a suspicion that you could. That's just a conjecture. Any questions about that? So in summary, what we did yesterday was almost right, but I butchered the integral of 2 du over u squared plus 3 at the end. I was in a hurry. We should never integrate in a hurry. Well, maybe in a test. But then be correct. Well, such is life. Okay, so the next order of business in here is error estimates for Simpsons rule and for the trapezoid rule. Now, your textbook also mentions an error estimate for the left and the right endpoint rules, but I don't have much to say about those. But that's also interesting, and they're actually even easier to work with. But the Simpsons rule and the trapezoid rule converge to the truth more quickly, let's say, as n increases. So the error in an approximation, what would it be? It would be the absolute value. I'm not sure he puts the absolute values here. It doesn't really matter too much. I mean, you might just say it's the difference. I usually think of this as being a positive quantity just for the sake of, my convenience, really. But I think the textbook might not do that. It won't matter to us. The point is either this or plus or minus this is E sub n upper S. I want to think about it being positive. All right. So the absolute value of the difference between Simpsons rule and the integral, what that is that's how far Simpsons rule is away from the truth. We're trying to calculate the integral exactly, right? Simpsons rule doesn't do that exactly, but it gives you a good approximation, right? That's the idea. This is how far the approximation is from reality. And likewise for the trapezoid rule, this is the error in the trapezoid rule of order n. for that integral. Now, if you take a course in graduate numerical analysis, or I don't know, maybe Dr. Wing might derive this in Math 352. Shout out for Math 352. You guys should take Math 352. It's a very good course. It's not that hard. Wait a minute. I don't believe in selling courses on their easiness. Strike that comment from the record. But I've heard rumors it's not that hard. And so Dr. Wing, we're trying to make that a yearly course. It's really important because Math 352 numerical methods is about how to use computers to actually calculate things, right? Which is maybe the thing you actually need to know for a job someday, possibly. It certainly got people fired, or excuse me, people hired, or not hired. Not being hired is not the same as being fired, but it kind of feels the same, you know. But definitely, Math 352 numerical methods it would be a resume boosting course to take. The course description and such might look a little unpleasant. I mean, it's the kind of course I would have avoided as a student, but that's because I like everything we were doing up till this point. But I know I have to teach you things I don't like because, well, that's my job. So, but that's just a question of personal preference. Now, some of you are here to get a degree so you can get a job. If you're such a person, you should seriously consider Math 352. It is a resume boosting course. All right, anyway. And it would certainly be a better choice for a higher level math course for the math minor than, say, Math 321, just as a comment. Sorry. I know. Too late? Yeah, sorry. I still don't know how you're taking Calculus 2 and Math 321 in the same semester. That ain't right. I need to fix that. There is a hole in our logic. I'm not saying anything in particular about your grade or anything. Don't misunderstand. I'm just saying about generally speaking, this is a course I would have liked to have. I will talk to linear algebra as if all of them have had this course already. All right. So anyway, I shut up. So these are the error estimates. These put bounds, like worst case scenario. The error in the Simpsons rule of order n could be this. The error in trapezoid rule of order n could be that. So here the b and the a are the upper and lower, the upper and lower bounds on the in the integral. F is the integrand. The m, this mysterious m, is a bound, an upper bound on the fourth derivative for a to b, for Simpsons rule. And for the trapezoid rule, you need to find a bound on the second derivative from a to b for m. Now, how do you find a bound on the fourth derivative or the second derivative of a function? How do you do that? I don't know. A lot of different answers to that question depending on the problem. I'm going to show you how to do it for a specific example related to one of your homework problems here in just a second. But this is it. These are the tools we have to work with. This is how we relate the error in Simpsons or trapezoid rule to a bound. That's what we know. Again, the proof of that is outside the scope of this course. But we will use these things. All right, so here's an example that I worked out a little bit earlier, and I'm nervous to erase because I'm afraid I'll get it wrong if I try to do it again. So I'll try to walk you through it in logical order. The question is this, number 5 from your homework. I'm not solving your homework problem, by the way. I'm adding discussion to your homework problem, okay? The homework problem asks you to calculate the integral from 0 to 1 of dx over 1 plus x squared as a means of approximating pi, either using the trapezoid rule of order 6 or Simpsons rule of order 3. Ignore the purple for now. All right? Let me put things in future bubbles. This is a future bubble. Don't look inside the bubble. What else is a future bubble here? Future bubble. Ignore. All right, I think that's enough. So my basic idea here is that we could use this integral, almost this integral, to define pi. Think about this. So you guys know this from Calc 1 or earlier this semester, right? The integral is inverse tangent of x from 0 to 1, but that's inverse tangent of 1 minus inverse tangent of 0. Whatever this thing called pi is, that should be pi over 4, right? I mean, you know that because you already have a definition for pi. Or do you? How do you define pi? It's what? 3.14159 672811357962009. Okay, I should stop, right? I was just saying numbers. I was just saying numbers. Nobody knows past about 5 digits. So you can just make them up. Nobody will call you on it. Hey. Actually, every once in a while, there's a certain subclass of people who have 10 digits memorized. They always get me. So, yeah. Most people don't know past 3.14159. It kind of rhymes. Okay, so my point to you is that if you didn't know what pi was, right, but you want it to be logically equivalent to this pi we've been working with, you could actually take this to be essentially the definition. Well, this wouldn't be an approximation. This would be straight up the definition of pi. Just think of it as a thought experiment. You could use that integral to define pi, right? I mean, you could. And from that viewpoint, we can also calculate this integral with a numerical method. And in fact, we can calculate it as precisely as we want, which means we can approximate pi as closely as we want by just taking n larger and larger. So that was what I wanted to do, was to look at this homework question number 5 and to try to use it to showcase the error estimate theorem over here for the trapezoid rule. So to actually show how that works, what do I need to do? How do I actually put this into practice? I have to find a bound for the second derivative, right? How do you do that? Well, short of other more clever ideas, you calculate the second derivative and try to say it's less than or equal to some number on the interval. Now, this may or may not be successful, this direct approach. Sometimes what I have to do is I have to go to the third derivative. And then for some reason, I'll be able to see that it's positive or it's negative on the interval. If I can do that, then that shows that the second derivative is either increasing or decreasing, which means that the endpoints for the second derivative will either be maximums or minimums. Was it? Oh. Future bubble. Yeah, we're not there. We're down here right now. So here's f of x. Here's the first derivative. Calculate the second derivative by quotient rule, right? So I get minus 2 from the top derivative. The denominator is 1 plus x squared squared. Ignore this green for a moment. And then minus and minus gives me plus 2x times the derivative of the bottom. Derivative of the bottom function, the denominator, is twice 1 plus x squared times 2x by the chain rule. Then I have to take the denominator squared. This is the quotient rule to get from here to here. At that point, I made a simplification. I'm like, wait a second. I've got a common 1 plus x squared everywhere. See it? Here, here, here. So if I factor it out of the top and divide the bottom, I reduce the power of 4 to the power of 3. I lose this one, and I reduce this square to just a plain factor. So in other words, the second derivative cleans up to this over here. It's 2 over 1 plus x squared cubed times minus 1 minus x squared. Distributing this minus, I factored the 2 out. And then I've got 2x times 2x, which is 4x squared. If you don't want to follow my calculation, you can just do it on your own, right? And you should get to the same thing. That was weird. let it think. Okay, so getting back over here. Are you guys with me to here? So I'm trying to calculate the second derivative because I'm trying to bound it. All right, finally, I get to this expression. 2 times 3x squared minus 1 over 1 plus x squared cubed. I don't think I can do much better than that. That's pretty simple. Let's try to analyze that in terms of inequality. All right, now I will erase the bubble. We are now to the bubble. I popped the bubble. All right. So here's my logic. If I'm trying to make a fraction, if I'm trying to put a bound on a fraction, right, I can divide and conquer in the following sense. I can try to make the numerator as, I can replace that with a number which is as large as this can possibly be. And I can replace the denominator with a number which is as small as it can possibly be. That should be a fraction which is strictly larger, or is greater than or equal to the given expression. Does that make sense? So what I do then is I think graphically. So like the top 3x squared minus 1, what's that? I mean, that's a parabola, 3x squared minus 1. It has y-intercept minus 1. It goes like this. So between 0 and 1, it's taking values between minus 1 and minus 1 plus 3, which is 2. So the largest the numerator can be is, the thing in parentheses at least, is just 2. So I put a 2 over here. Make sense? The denominator, on the other hand, 1 plus x squared, what's the smallest that can possibly be? 1. Right, so I replace this 1 plus x squared with 1. And there you have it. A bound on the second derivative for this integrand is 4. Let me let you digest what I just said there. How do I what? Oh, because if you look at 3x squared minus 1, that goes between minus 1 and 2, if you put in 0 to 1. Grounds. Sorry. What's up? That is the idea. I mean, that's one way. Sometimes this works. Other times you need other ideas. But that's generically speaking a game we can play to try to find a bound. Now, there are other games. Some games are easier than this one. So that makes m equals to 4. All right, so let's then use the theorem, right? Right here. So the error in the trapezoid rule of order 6 should be less than or equal to 1 cubed divided by 12 n squared, which is 6, because that's what was given in the problem, times 4, because that's what we just figured out m was. So you work that out, you get the 4 cancels, you get 3 times 36, which is 108. So the error in the trapezoid rule for the integral would be 1 over 108. I actually am more interested in what? I'm interested in 4 times the trapezoid rule, honestly, because I don't really want to calculate this integral. I'm really more interested in 4 times the integral in this particular problem, right? So if you think about this, 4 times the trapezoid rule minus pi should be bounded by 4 divided by 108. You just multiply the error. If you have a bound of epsilon for the integral of f, if you take c times f, where c is a positive constant, the new error would be just c times epsilon, because we're talking about absolute error. It's just multiplicative. So this analysis tells me that if I take 4 times the trapezoid rule, order 6, and subtract pi, I should be within 0.037 of the actual value of pi. All right? So I'll try to show you in a second here, but if you use a some technology to calculate trapezoid's rule of order 6, what you get is 0.784241. If I multiply that by 4, I get 3.136964. If I subtract actual pi, 3.14159, nonsense I make up, you'll get 0.0046. As you can see, we are well within the claim of accuracy. In fact, we're closer by about 10 times, right? 0.004 versus 0.03. We actually have one more significant digit than the the error estimate says. The reason for that, if you read section 8.7 carefully, they actually have stronger theorems than this. Instead of having an m, they actually have the fourth derivative evaluated at a particular c, and the second derivative evaluated at a particular c between a and b. Sort of analogous to the mean value theorem. There exists a c such that the error is actually attained by a particular value c. So if you can find that, that would give you the strict bound. But I think kind of begs the question. I mean, pragmatically speaking, I think you have to use the kind I wrote up here as opposed to the ones that evaluate at a particular c, which you'll see when you, when you read the section. Or not. I mean, no, read the section. Read the section. Let's see here. So that's pretty cool. I mean, we could calculate pi, and well, I didn't do it. It's not, you could, if you had 10 minutes and some scratch paper, you could reproduce this with hand-to-hand combat with arithmetic. It's not something you couldn't do. I just am lazy, so I use technology. All right, let's see if I can show you. I sent you a couple links. After like 5 whole minutes of Googling, I found for you programs. It was very hard. Come on. Here's the one that's useful to us. It was the second email, the deeper Google. And so here, what I have done, now this one's actually set up for Simpsons rule. You might be able to find one that's a better interface. This works. It's not the prettiest thing, but so 1 over 1 plus x squared is the integrand. I'm integrating from 0 to 1. And here's the thing that's awkward. To figure out what n is, I kind of have to work backwards. Like, so if I want n equals 6, the interval width has to be 1/6, right? That gives me 6 intervals in 0 to 1. I mean, that's kind of, I'm not super happy about that. I'd rather be able to just put in n equals blah. Oh well. I didn't have to program anything for this, and I didn't have to put any numbers in, so I will shut up and be happy that it did this for me. Anyway, here you go. Left, right, midpoint, trapezoid, Simpsons, this guy. I mean, logically speaking, we shouldn't ignore him, but I'm sorry about that. That was awful. Let's see here, trapezoid rule, that's where I got this number, right? And there's the absolute error is actually 0.001. So this, could you guys tell me what 1 over 108 is? What is this? What's this value? What's 1 over 108? Can you tell me, somebody? Decimal? Okay. So, 0, 0. I was about to get really confused. Thank you. 0093. See here, the actual error is 0.001. So we're 9 times. I mean, depending on how this m we've come to, right? The harder you work at finding a good m, the better your error estimate, right? If you're kind of, I don't know. That's the thing that makes this a little bit ambiguous, is some people might find a tighter bound than others. The bound is, the closer the bound is to being optimal, the tighter it is. I mean, if you actually have a value, I think actually the word, to be more precise, if you can find something in the interval where the m is actually attained, that's the best you can do, right? If I could find that f prime of a half was equal to 3, then I couldn't do better than 3, probably. Well, yeah, I can't have 2.9 because then 3 would be bigger than it. All right. Anyway, so your homework partly is to calculate Simpsons rule, trapezoid rule for various orders. You're welcome to use the website just to do it. I don't mind that. That's fine. But there are other parts of your homework in the numerical methods which are about applying these theorems. There you're actually going to have to do some hand-to-hand combat with equations and such. So now there's another kind of problem that you face in section 8.7. me see if I can work one of those, and then I'll take your homework questions. Let's see here. Duh. Sorry. By the way, I'm taking my book back from the math department, so if you want it, you have to come to my office hours. I was leaving it with the secretary, but I decided I'm taking it back, so. I don't think any of you are really using it over there, so it's kind of a moot point. I'm just saying for the sake of communication. All right. Is there a page missing from my book? What's going on here? Oh, duh. It's like 8.7 and then review exercises. I was trying to understand the review exercises being the 8.7 exercises. It's very confusing. Okay, so here we go. Can I erase this? Are we okay on this? I mean, oh, stupid thing. Turns out there's another way to define pi in terms of calculus, which is probably better than what I just did here, but that's for another day. So here's the question, something like this. Determine values of n which guarantee a theoretical error less than epsilon if this integral is estimated by a trapezoid rule or Simpsons rule. Let's see here. I'll do number 17. Let me do number 19. It's a little bit more interesting. So we have the integral from 1 to 3. I mean, 17 would make a nice test question because the bound analysis is, well, I don't know. Let me not start talking about that. So e to the x, I want to calculate this integral, which is kind of silly because of course we can do it, right? But if you want to calculate this integral to within epsilon equals to 0.01, the question is what n needed for Simpson's rule or the trapezoid rule of order n to have so we have ESN, ETN. Fine. All right. Well, I mean, equal to. We want to. The goal is to find the smallest n which works, right? So how do you attack this kind of problem? Yes, sir. Yeah, sure. So what we're asking is, what value of n do I need to take in order that Simpson's rule of order n or the trapezoid rule of order n approximates the integral from 1 to 3 of e to the x dx within 0.01. So we use the theorem basically. So what you want to do is, well, first we need to find bounds. So here f of x, I mean, the bounds are kind of silly. F of x is equal to e to the x. So guess what? F prime of x equals f prime prime of x equals f prime 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 of x equals f prime, 4 of x equals e to the x, right? And so forth. All right, so in fact, the function and its derivatives are strictly increasing everywhere. Why is strictly increasing so nice? Think about this. If I have g, y equals g of x strictly increasing, like that, right? If you take, say, a and b, what do you get to say about g of a and g of b? Right? If g is increasing, increasing function preserves inequalities. That's what an increasing function does. So, among other things, if I think about 1 less than or equal to x less than or equal to 3, well, guess what? I have e to the 1 is less than e to the x is less than e to the 3. So, long story short, I can use that the second derivative of x is less than or equal to the e to the 3. That gives that's an m. Theoretically, this problem is very, very silly because the calculation that we're being asked to do necessitates knowledge which makes the exact answer immediate. So, like, don't think about this problem too hard about what it means numerically. But it's a good homework problem because, hey, this, what do you think? Is this or what I just erased here? Right? I mean, this is way, way easier to think through. That's the point. That's why this is a homework question. How about this would give us a good m, right? Bound on the second derivative for the trapezoid rule. But you know what? It also works in this case for what? This also will serve as a bound on the fourth derivative from 1 to 3. All right? Upper bound, of course, is what I'm talking about. So then we use a theorem which says that, let's see here, what we got? I'll start with the trapezoid. Etn is less than or equal to what? Let me write it symbolically here for a second before I put the numbers in. b minus a cubed, right? Times m divided by what? 12n squared. And the error in Simpsons rule of order n is less than or equal to what was it? b minus a to the 5th power times m divided by, well, obviously 2,880 n to the 4th. I mean, come on, isn't it obvious? I have no idea why that number's there. It's an interesting number, though. N to the 4th. I mean, you can see right here why Simpsons rule converges faster than trapezoid rule, right? This, in terms of, steps, 1 over n to the 4th is getting smaller a lot faster than n squared, right? So that's why Simpsons rule is probably a better bet. All right. Anyway, so let's see here. What do we got? Markers that are dry out. For enough of these. So you guys put in the number. What do we get? Yeah, 8 e cubed divided by 12n squared, right? And this one is what? This is, what is it? 32 e cubed. Now it's a quirk of this example. We can use the same m for both of these. Usually they have to be different, right? Usually the second and the fourth derivative aren't the same function. This is a special case. So 2,880 n to the 4th, and then what do you want to do? Well, you want to basically put this equal to what? .01, right? That's our target. So can you solve those? Yeah, sure. This is what? This is n squared equals to what? 80 cubed divided by 12 times 0.01, right? So therefore n, something like square root of 8e cubed divided by 12 times 0.01. And the other one, I get n to the 4th is equal to 32e cubed divided by 2,880 times 0.01, right? So I got to take the fourth root this time. What's that give us? You're like a headache. Let's see here. No, let's see here. That was not the question answer I was looking for. Not natural log. Stupid calculator. E to the 3 divided by 12 divided by 0.01 square root. I get 36.6 for this, roughly speaking. For the second one, so you guys can check me on that. Hmm. 2.17. Golly. So that suggests what? I mean, of course, those are not the answers, right? Can you do 2.17 iterate, Simpsons rule with 2.17 intervals? Can you do trapezoid rule with 36.6 intervals? No, what do you do? Round up. That's right. Go one more. So 3, Simpsons rule with order 3, and the trapezoid rule with 37 should do it. Now, here's the moment of truth. I worked problem 19 in section 8.7, which means we can check the answer in the back of the book. I'm not super thrilled about doing this. This could go badly. Let's find out. Moment of truth. What were we? Number 19? Oh, phew. It says n greater than or equal to 37 and n greater than or equal to 3. Yay, math. Okay, so did I tell you guys that if I was in Star Wars, I'd probably be Sith? As mathematicians, we only deal in absolutes. I'm not actually a mathematician, but it seems like a stupid thing to say. Yes.
Why didn't we take the product of both error and then compare it to 0.01?
Why would I do that? I mean, the question here is what n do I need to make sure my error is smaller than 0.01? The thought process here is kind of opposite. Like the initial example I did.
Is that a comma or is that a product?
These?
No, in the question. What n?
That's a comma.
No, they said.
That's a comma.
Oh.
A badly written comma. Ah!
I thought it was a product side.
So you know min.
Huh?
You know min?
Yeah.
Yeah, this is exactly the kind of thing min would do. Except he would do it on a test and then he would try to solve that problem. That much more fantastically complicated problem. It's very aggravating to me sometimes. Min has a lot of ability, but sometimes not much common sense. I'm not saying that you. I'm not trying to insult you. I'm sorry. I think I'm going to stop digging this hole. But no, it was supposed to be a comma. Yeah. No, I don't even know. I don't. Oh my goodness. The product of those being 0.01. Oh, there are infinitely many answers, because you can make the one smaller and the one larger. many, 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 many solutions to that. That would be, no.
Find at least 20 of these or something.
What's that? Oh, here. What was this one? What did we just do? It was integral of e to the x, right? Maybe it's exponential of x in this thing. And then what was it? Integral from what to what? 1 to 3? And let's see here. What was the, what did we advocate for Simpsons rule? 3? Oh, 3 minus 1 divided by 3 is 2/3. I know, right? And it took me like 5 whole minutes to find this in Google, too. It's a lot of my time. Is it still thinking? Hey. Well, that's disappointing. Aw. Stupid Wolfram Alpha. So inconsistent. This is something built over Wolfram Alpha somehow. Anyway. I'll put that away. This one was also nice. I like this one. This one's really nice to visualize. Try to make it bigger. I sent you guys a link to this, but just to look at it for a second. And then I'll do your homework for you. I mean, help you with your homework. Yeah. So this is an illustration of trapezoid rule, which is kind of hard to appreciate with n equal to 10. But if I go to like n equal to 5, and you still can't see it very well. You can kind of see, though. You can see it. Maybe if I change the function. X squared's too boring. How about that? Ooh. So there's the trapezoid rule. Still kind of hard. Oh, n equals to 20. No. We want to be yuckier. There we go. See, there you go, trapezoid rule. Compared to, say, midpoint rule. Ooh. Compared to left. Compared to Simpsons. You see, I mean. So Simpsons rule, okay, so you have to interpret that. What it's doing is it's overlaying the approximating parabolas on each interval and like showing you them. You stare at it for a while, you'll see what it's doing. It is, because it's showing the parabolas, it's extending the parabolas on each approximating region past their approximating region.
So what happens if you do like n equals 20 with Simpsons?
We only can go to 10, apparently. But it's going to show all the parabolas. I don't know. If I were doing this, I would want to cut those parabolas off on the intervals. But, you know, it's as good as the money I paid for it. So, no, I did not pay for it. But on the other hand, at least it worked. Like I tried to do the thing in the Wiley Plus, and it, I don't know, it didn't like my Java or whatever, and I have zero patience to fix these sorts of things when I can Google for 5 minutes and find one that sort of works. So anyway, I shut up. Can I put this away? So play with this if you want to see more examples. Use the one to calculate if you want. You can implement any of the algorithms directly in Wolfram Alpha using sum notation like I showed you last class. It's really up to you. All right. So now that we got that out of our system, we still have a half hour left, thankfully, for your homework questions, which hopefully won't be about this stuff. Ha ha ha. This problem of bounding an expression is something that will come back to us again. So it's worth your attention now, because it's going to keep coming up. But I don't know. I mean, so we'll come back to it, because the problem of, you know, saying how close an approximation is to something else is something that we will look at again. with other things. So what's your question? Surely someone in here has a question about homework. Yep.
Can you do 8.641?
I can try. Let's see here. Ooh, interesting. And it tells us what? It says try what? U equals to, what is it? Tangent of x over 2, is that right? Is that right? (41) in section 8.6. Interesting. See, that is not what I would have tried. I mean, left to my own devices, I would let u equal hyperbolic secant plus hyperbolic tangent, and then hopefully the argument like for secant works in the hyperbolic case the same. But the book has told me to do this, so let's try it. Now, so we have to go back to our triangle idea, right? So we really, to get started, we have to repeat this song and dance over here, but for the hyperbolic case. So you guys will have to help me through this. If I put x over 2 here, right, then I put u here and 1 here. What is this? Remember the relation in the hyperbolic triangle is different. Square root of 1 minus u squared. Okay, let me check that. So like cos squared minus sinh squared is the square root. Okay, yeah. I agree. Okay, good. Now, so like cos of x over 2 is what? All right. What's sinh of x over 2 is what? U over that, right? Now, can you guys remind me, what are the double angle formulas for cos sinh? I mean, I think it's the case that the sinh of 2 theta is twice cos theta sinh theta. What's the identity for the hyperbolic cosine of 2 theta? I don't remember right offhand. Let me just try to work from the definition. 1/2 e to the 2 theta plus e to the minus 2 theta. Oh, okay. I mean, there's an adding 0 thing that has to happen there. It's not terribly natural. So what's the identity here? Oh, wait a minute. I'm working too hard. Differentiate, right? So if I differentiate this, I get 2 cos 2 theta equals to 2 cos squared theta plus 2 sinh squared theta, right? Which is what? How can I convert this to cos squareds? Or to sinh squared? You pick it. I don't care. Cos squared theta minus sinh squared theta is 1, right? So sinh squared theta is what? This is really 4 cos squared theta. Minus 2? Okay. Anyway, getting to the point, and you guys tell me if I'm wrong. Is that correct?
Yeah.
You guys got to keep me on the straight and narrow here. I'm gonna, if you don't mind, I'm gonna write that. Well, fine.
I don't think it's for cos.
Yeah, I differentiate.
Plus 2 cosh.
I differentiated to get from the. Okay, so now let me box. So we have these identities. It's fine. So we have these identities. Let me call them star and star star. So you take star and you take star star. And you put theta equals to what? Theta equals to x over 2 for star and star star. What do we get? We get sinh x is what? Cosh x over 2, right? Sinh x over 2, which is really what? Two u over 1 minus u squared, which is an awful lot like what happened over here. Just instead of having 1 plus u squared, we have 1 minus u squared for the sinh x. Cosh x, what do we got there? We've got 2 cosh squared of x over 2 minus 1, which is what? That's 2 over 1 minus u squared minus 1. So just like with the cosine, we're going to have to make a common denominator to find the formula, which is analogous to the one that's boxed over here. So you got yourself a 2 minus 1 minus u squared over 1 minus u squared, otherwise known as, weird. Oh, no, not too weird. 1 plus u squared, right? Is that right? All right. Okay, so now we've got ourselves our cosh x formula, right? We've got our sinh x formula. What else might I want? Yeah, du, we'd like to know that. How do you get du? I mean, any number of ways, right? You differentiate any of these to get du. I'll go back to the original one. So du is 1/2 hyperbolic secant squared of x over 2 dx. So that means 2 du is equal to, and let's see, hyperbolic secant squared is what? Yeah, dx over cosh squared of x over 2, which is, well, that's multiplication by 1 minus u squared. Okay, so finally I get 2 du over 1 minus, and I think, if you were lazier and reckless, you can derive one of these and go back over to this and go, oh, okay, so it's just going to be put a minus here, here, and here. But then you would have got this wrong. All right, anyway, so there you go. Now, what do we do? Now that we have taken our toys out of the box, now let's use them. Hyperbolic secant of x dx is what then? That's dx over, what is it, cosh, right? What is it?
The former was a 2.
Uh-oh. Oh, 2 minus 1 is 1. But then minus a minus is a plus. That's okay. Excuse me. Oh, here we go. So we got ourselves a, what was dx? Oh yeah, 2 du divided by 1 minus u squared all over cosh x, which was what? 1 plus u squared over 1 minus u squared. So obviously we can change this to 2 du, right? divided by 1 plus u squared. Heh. So, yay. There is a light at the end of the tunnel. Obligatory, it's not the train. Let's see here. 2 times inverse tangent of u plus a constant. And I think I've almost solved your problem. Sorry if I have deprived you of the joy. Hyperbolic tangent of x over 2. Golly, what kind of answer is that? Man. That is, yeah. What's that? Well, it is 41. I think you can check the answer in the back of the book too, right? Sure, yeah. But I think on the test, an easier way to do it would be just set u equal to the hyperbolic secant of x plus the hyperbolic tangent of x, like this. See, because if I do that, then like du is what? What's the derivative of hyperbolic secant? Is this the one that's minus? Huh. Well, that's going to be a problem, isn't it? I don't think this quite works because then that's what minus, you see that's minus secant tangent? I think for this reason I should put a minus here. I think if I put a minus before the secant for the u substitution, it worked out better. Then I get secant plus, oh, but then, oh, so maybe my my usual secant substitution doesn't work here. I mean, I had hoped it would work, but I'm not really optimistic that the usual u equals secant plus tangent works here now. Huh. Maybe we have to do this. I don't know. These Weierstrass, the Weierstrass substitution and the corresponding hyperbolic Weierstrass that we just discovered, these are like sledgehammers. They will bust up anything that comes in your path. So, I mean, there's a variety of questions that I could ask that you could do using less complicated methods. I mean, a great example is the secant integral, you know? Integral of secant theta d theta, right? Now, the way I showed you to do that was that's the integral of du over u, right? So that's the natural log of the absolute value of secant theta plus tangent theta. We did that about a week, 2 weeks ago, I don't know. We did it sometime, so can't be that long ago that we did it. That was from u equals secant plus tangent, right? In view of the Weierstrass machine, this is the integral of d theta over cosine theta, right? And so you're like, aha, well, fine, you're in my house now. And Mr. Weierstrass says that's 2 du over 1 plus u squared. Divided by cosine theta, which is 1 minus u squared over 1 plus u squared. Right? So you get integral of 2 du over 1 minus u squared. And you're like, aha, I will partial fractions that. That is 1 over 1 plus u, or rather 1 minus u, plus 1 over 1 plus u. I mean, obviously that's the partial fractions, right? I'm being facetious. If you work it backwards, though, you can see I'm right. Make a common denominator. 1 plus u here. Oh, minus. Minus. So that when you make a common denominator, you end up with a 1 plus u here, a 1 minus u here. The